Hello everyone, welcome to the session on digital electronics. In this session, we'll be discussing about sequential circuit called as SR flip-flop. In this session, we will see initially what we mean by sequential circuits. Then we will go for the simple SR flip-flop. Then we will go for the clocked SR flip-flop. And finally, we will see what we mean by the preset and clear inputs of SR flip-flop. Friends, as you know that you are viewing this session on my YouTube channel, Learn with Prakash Khanoi, and subscribe to the channel to see many videos on the subjects of electronics and computer science. So we will start the session what we mean by sequential circuits. Now earlier we have discussed combinational circuit, and in case of combinational circuit, the output will depend upon only the input that is being present. There are different combinational circuits such as multiplexers, demultiplexers, encoders, decoders, adders, subtractors. All these are the combinational circuits. And in case of these circuits, we have been observed that the output of the circuit will only depend upon the input that is being present in the circuit. So we can say that in case of combinational circuit, the current will flow from one end and at the input of the circuit, and it will be taken out at the output of the circuit. So combinational circuits are such circuit where the values cannot be stored, or combinational circuits are those circuits where they cannot retain any values. So whenever you want to retain some value, that is whenever you want to build some memory, then it is necessary that you can make the use of the sequential circuits. So you can say that the sequential circuit is a kind of a combination of combinational circuit and some memory element, where the output of the combinational circuit is fed back to some memory element, and the output of the memory element is being fed back to the combinational circuit. So in case of sequential circuit, the input will accept the input current and there will be an output current, but some part of the output current is fed back to the input again, and therefore you can say that there is a kind of a loop. Sequential circuits can be used whenever we want to build one bit storage element. That is, whenever we want to store a binary bit of 0 or 1, then in such a case we need to make use of the sequential circuits. So one can easily observe that the sequential circuit may also have a clock input, while the combinational circuits cannot have a clock input. So whenever we build a one bit storage element, then we can combine and we can have a group for n bit storage. So it is possible that by making the use of the sequential circuit, you can store the n bits. The circuits which can store one bit of information, they are being called as the flip-flop because they can flip from one state to the another state. That is, either they can have the output equal to 1 or they have the output equal to 0, and therefore they can be called as the flip-flop circuit. So we can say that the circuits of flip-flops or the circuits of counters or the circuits of shift registers, all these are the sequential circuits. And in this part of the digital electronics, we'll be discussing all such sequential circuits. Now we will go for the discussion of the sequential circuit. So the simplest type of the sequential circuit is the one bit memory cell. So one bit memory cell can be easily constructed by making the use of the two NAND gates connected as shown in the figure. So one can easily observe that the input of the first NAND gate is connected to the output of the second NAND gate, and the output of the first NAND gate is connected to the input of the second NAND gate. And one can easily observe that the NAND gates which are used here are just nothing but the NOT gates. So such a circuit is being called as a NAND latch. And by using the NAND latch, it is possible that we can store one bit of information, and therefore the NAND latch is being called as a one bit memory cell. So you can say that it is a basic flip-flop, And such flip-flop can be constructed by making the use of the two NAND gates which are connected as shown in this diagram. So as shown in this diagram, we are using two gates, gates G1 and G2. The output of the G1 is connected to the input of the G2, and the output of the G2 is connected to the input of G1. So in this NAND latch, since it is a basic circuit, there is no provision of applying the external input. So this circuit, one can easily understand, this circuit will have the two states. That is, the either the output Q will be equal to 0 or the output Q will be equal to 1. So initially we can assume the output Q is equal to 0, and therefore when 0 is connected to the input of the G2, then the output Q bar will be equal to 1. And the output Q bar is connected back to the input of the G1, and therefore it will confirm that the output Q is equal to 0. So one can easily observe that the outputs of both the NAND gates are never equal. They are opposite to each other, and therefore these outputs are called as Q and Q bar or Q complement. Now, this circuit has the two states, and both the states of this circuit are the stable state. That is, when this circuit is in one state, then it will continue to remain in that state only, and it will not change the state on its own. And this property of this circuit is being called as a memory, and therefore we can say that this circuit is a 1-bit memory cell. Now we will go for the SR flip-flop. Now earlier we have seen the circuit of the NAND latch, and in case of NAND latch, one can easily observe that there is no provision of applying external input, but it is necessary to connect some external input to the circuit so that we can store whatever the bit we want to store in the circuit. And therefore we can modify the circuit of the NAND latch, and such flip-flop is being called as the SR flip-flop or set reset flip-flop. So SR flip-flop, you can say that it is a circuit which will have the two inputs. The first input is being called as the set input S, and the another input is being called as the reset input R. So one can easily modify the circuit of the NAND latch in order to construct the SR flip-flop. Now instead of using only 2 gates, here we will make the use of the 4 gates. And one can easily observe the change in the connections. Observe that the set input S is applied to the gate G3, where G3 works as an OR gate. The output of G3 is connected to the G1, one input of G1. The reset input R is applied to the gate G4, where G4 also works as an OR gate. The output of the G4 is connected to the one input of G2. Also, one can easily observe that the output Q is connected to the another input of G2, and the output Q bar is connected to the another input of G1 as shown in the figure. So whenever we want to represent this SR flip-flop, then this SR flip-flop can be represented by a symbol as shown in this diagram. So a flip-flop can be represented by a block where it will have two inputs, S, that is the set input, R, that is the reset input, and the outputs will be Q and complement of Q, that is Q bar. So by using 4 NAND gates, it is possible that we can construct the SR flip-flop. Now we can easily prepare the truth table of SR flip-flop, and the truth table of SR flip-flop will look like this. So when both the inputs S and R are equal to 0 and 0, then one can easily observe that the outputs of G3 and G4 will be equal to 1. Now, in order to understand the working of any sequential circuit, it is necessary that we should consider some initial state of the circuit. So initially, we can suppose Q is equal to 0. And when Q is equal to 0, the 0 will be connected over here. And therefore, the output Q bar will be equal to 1. So when 1 is connected to the input of G1, then one can easily observe that both the inputs of the gate G1 are 1. And therefore 1 into 1 is 1, that is its complement is equal to 0, and therefore the output Q will continue to remain 0. That is, when S is equal to 0 and R is equal to 0, then there is no change in the initial output of the circuit. If it is 0, then it will continue to remain 0. If it is 1, then it will continue to remain 1. And therefore, this state of the SR flip-flop is being called as a no change state of the SR flip-flop. When S is equal to 0 and R is equal to 1, then one can easily observe that the output of the gate G4 will be equal to 0. And therefore, when any one of the input of the NAND gate is equal to 0, then 0 into 0 is 0, and therefore the output of gate G2 will become 1. When it becomes 1, then the input of both the gates G1, both the inputs of the gate G1 will become 1, and the output Q will continue to remain 0. So if the output Q is initially 0, then it will continue to remain 0. If the output Q is initially 1, then it will get converted into 0. And therefore, when S is equal to 0 and R is equal to 1, the output Q will become 0 and Q bar will become 1. And this state of the SR flip-flop is being called as a reset state, because the output Q becomes 0, and therefore this state is being called as a reset state. When S is equal to 1 and R is equal to 0, then one can easily observe that the output of the gate G3 will become 0, and therefore the output of gate G1 will become 1. That is, whatever may be the initial output Q, it will get changed and it will become 1 now, and Q bar will become 0. And therefore, this state of the SR flip-flop is being called as a set state, because the output Q is becoming 1 whenever S is equal to 1 and R is equal to 0. Now, when we check for the last state, that is when S is equal to 1 and R is equal to 1, then one can easily observe that the outputs of both the gates G3 and G4 will become 0. If any one of the input of the NAND gate is 0, then we know that its output will become 1. So in this case, both the outputs Q and Q bar will become same, and that they become equal to 1. But this is against our logic, and therefore this state is not allowed in SR flip-flop. That is, when S is equal to 1 and R is equal to 0, then this condition or this state of the SR flip-flop is not allowed. And this is, you can say, is a kind of problem with SR flip-flop, that this state, we cannot make use of it whenever we make the use of SR flip-flop in any logic circuit. Now it is possible that you can apply some clock input to the SR flip-flop. A clock input can be applied to the SR flip-flop, and by using the clock input, it is possible that we can store the data at particular instant to get stored into the SR flip-flop. So the clock input is the another input, and whenever the clock is enabled, then only the flip-flop will be enabled, and we can store the data in the SR flip-flop. So we can modify the circuit of the SR flip-flop so that we can apply the external clock input to the SR flip-flop. So you can say that the clocked SR flip-flop will now have three inputs, that is the set input S, reset input R, and another input that is being called as a clock input, where we can apply the clock pulse. So clock pulse is just nothing but a square pulse. So we can apply the square pulse, and whenever the square pulse is applied, then the clocked SR flip-flop will be enabled, and we can store either 0 or 1 in the SR flip-flop. So this is the circuit for clocked SR flip-flop, where one can easily observe that the clock input is applied to the gates G3 and G4, while the set input is applied to the gate G3 and the reset input is applied to the gate G4. So whenever this clock is high, then only the gates G3 and G4 will be enabled. If this clock is equal to 0, then the gates G3 and G4 will not be enabled, and therefore in that case you cannot make the use of SR flip-flop to store the 1 bit of information. So this is a symbol for clocked SR flip-flop. So one can easily observe that here the clock input is applied to the SR flip-flop. So whenever we think of a clock input, then instead of a set and reset input, one can think of Sn and Rn, where Sn will denote the input during the bit time n, and Rn will denote the reset input during the bit time n. And whenever we think of the output, then output can be think of as Qn plus 1, that is the output after the application of the clock pulse. Therefore, we can write the truth table for the clocked SR flip-flop as input Sn and Rn and output Qn plus 1. So when Sn is equal to 0, Rn is equal to 0, then the output Qn plus 1 is equal to Qn. That is, whatever is the initial state, that will continue to remain, and there will be no change in the state of the SR flip-flop. Whereas Sn is 0 and Rn is 1, then the output Qn plus 1 will be equal to 0, and this is the reset state of the SR flip-flop. When Sn is equal to 1, Rn is equal to 0, then the output Qn plus 1 will be equal to 1, and this is being called as the state condition of SR flip-flop. And when Sn is equal to 1 and Rn is equal to 1, then this state is not used in case of SR flip-flop, because both the outputs Q and Q bar will try to become same, and this is against our logic. So one can easily observe that there is no change in the truth table of the SR flip-flop. The only thing is that here we have made a provision of applying the clock pulse, and so that whenever we apply the clock pulse, then at that instant the data will be stored in the SR flip-flop. It is also possible that you can apply the preset and clear inputs to the SR flip-flop. These inputs are used to set the initial output of the SR flip-flop. Now, so far, we were not having any control on the initial output of the SR flip-flop. But many times we want the output either equal to 0, initial output either equal to 0 or equal to 1. So whenever you want to set the output of initial output of SR flip-flop, then it is necessary that you can make the use of preset and clear inputs. So clocked SR flip-flop can be modified so that we can apply the preset and clear inputs to the SR flip-flop. Now in this case, the SR flip-flop will have the three inputs: set input, reset input, clock input, preset input, and clear input. So the circuit with preset and clear for SR flip-flop can be shown as shown in the diagram. Observe that the gates, the first two gates will have the same configuration. Only the thing is that the preset is being added to the gate G1, and the clear is being also added to the gate G2. So by making the use of this preset and clear, we can set the initial output for the flip-flop. Say for example, when preset is equal to 0, then the output of this gate will be equal to 1, because we know that when any one of the input of the NAND gate is equal to 0, then 0 into anything is 0, and its complement will be the output, that is 1. So whenever you want to set the output Q equal to 1, then you can apply 0 to the preset input. Whenever we apply 0 to the clear input, then the output Q bar will become 1 and Q will become 0. That is, whenever we want to reset the output Q equal to 0, then you need to apply 0 to the clear input of the SR flip-flop. So preset and clear inputs are used only initially to set the output Q equal to 0 or 1. Otherwise, for normal working of the flip-flop, both the preset and clear are kept at high, that is logic 1. And one can easily observe that the preset and clear are activated when 0 is applied to them, and therefore these inputs are called as the active low inputs of the SR flip-flop. And therefore, whenever we draw the symbol for the SR flip-flop, then for the preset we use the bubble, and for clear also we make the use of the bubble. So they indicates that the preset and clear are active low inputs, and they are used to set the initial output Q either to 0 or 1. So as I told you, when preset is equal to 0, then the initial output Qn plus Qn becomes 1, and when clear is equal to 0, then the initial output Qn becomes equal to 0. Now one can easily observe that both preset and clear cannot be set to 0 simultaneously, isn't it? When preset is set to 0, clear must be high. When clear is set to 0, then preset must be high. And for normal working of the flip-flop, both preset and clear must be high. So there is no change in the truth table of the SR flip-flop. Because of preset and clear, there is no change in the working of the SR flip-flop, and the truth table of SR flip-flop will remain the same. That is when S is equal to 0, R is equal to 0, Qn plus 1 is equal to Qn, that is there is no change in the state of the SR flip-flop. When S is equal to 0, R is equal to 1, then Qn plus 1 is equal to 0, and this is the reset state of the SR flip-flop. When Qn Sn is equal to 1 and Rn is equal to 0, then the output Qn plus 1 is equal to 1, and this is the set state of the SR flip-flop. And when both the inputs Sn and Rn are equal to 1, then this state cannot be used by the SR flip-flop, because both the outputs Q and Q bar will try to become same, and this is against our logic, and therefore this state is not used in SR flip-flop. So thank you friends for viewing the session. Hopefully you have understood what we mean by sequential circuits and the working of SR flip-flop. Thank you all for viewing the session.